You ever wonder how old-school electronics, like that classic speak and spell, actually learned how to talk? It wasn't magic, and it definitely wasn't some tiny record player inside. No, it was this brilliant piece of signal processing called Linear Predictive Coding, or LPC. Today, we're going to pull back the curtain and look at the fascinating tech that gave computers their very first voice.
So you have to put yourself back in that time. The central question they had to solve was, how do you teach a computer to talk? I mean, how do you take the incredible, rich complexity of a human voice and boil it down into a tiny set of numbers that a simple 16-bit chip can actually understand and, spit back out as speech?
Well, the secret, it turns out, lies in this wonderfully simple model of how we ourselves speak. Just picture our speech as two totally separate parts. First, you've got a sound source. Think of it like a simple buzzer. And then you have a filter, which is basically a tube that shapes the sound coming from that buzzer. That's it. It's called the source-filter model, and it is the key to absolutely everything we're about to talk about.
So here's the game plan. We're going to start with that simple but really powerful buzzer and a tube idea. Then we'll dive into the math puzzle of predicting sound. After that, we'll uncover the really elegant autocorrelation solution and tackle the engineering headache of keeping the filter stable. And finally, we'll see the magic happen as a simple buzz gets turned into actual recognizable speech.
All right, let's get right into it with that core analogy. It's way more intuitive than you might think.
Okay, so the source part, that's basically our vocal cords. For sounds with pitch, like when you say ah, it's a periodic buzz. For sounds without pitch, like s, it's more of a noisy hiss. Now the filter, that's our vocal tract, our throat and mouth. It acts like a resonant tube. As we change the shape of our mouth, we change the resonant frequencies of that tube. Those peaks are called formants, and they're like the acoustic fingerprints that let our brains tell the difference between vowel sounds.
Okay, so that physical model's great, but how do we turn it into math that a computer can actually use? This is where the predictive part of linear predictive coding really comes into play. We need a way to describe the shape of that tube using just numbers. And the idea is just so clever. See, human speech isn't random noise. It's super predictable from one moment to the next. LPC totally takes advantage of this. It basically says, hey, we can make a really good guess about the next digital sample of a sound wave just by looking at a few of the samples that came right before it. It's like a prediction game.
And this right here is the machine that does the predicting. It takes a handful of past samples, say 10 or 12 of them, multiplies each one by a special weight, and then adds them all up to guess what the next sample is going to be. Those weights, they're called predictor coefficients, and finding the perfect set of these coefficients is the entire goal here, because those numbers are the mathematical recipe for our vocal tract filter. They are the shape of the tube, just written in math.
So the big question is, how do we find those magic coefficients? We can't just guess, right? We need a bulletproof way to pull them right out of the speech signal itself.
And the solution is this beautiful three-step mathematical dance. First, we calculate something called the signal's autocorrelation. Then, we use those results to build a special set of linear equations. And finally, and this is the best part, we solve them using this incredibly efficient algorithm that was just perfect for the limited hardware they had back then.
So what even is autocorrelation? How do you measure how predictable a signal is? Well, picture this. You take a copy of the signal and you slide it over the original, one sample at a time. And at every single step, you measure how well the two line up. When you get a strong match, that tells you found a repeating pattern. It reveals the fundamental rhythm and redundancy in the sound, which is exactly the info our predictor needs to make its guess. Now, when we use these autocorrelation values to build our equations, something really neat happens. This beautiful, supersymmetric structure emerges, called a Toeplitz matrix. Just look at it. See how every diagonal has the exact same value all the way down? This isn't just pretty to look at. This special structure is the key that lets us solve the whole system without having to use tons of computing power. And this is where the real breakthrough came in. Instead of some massive, slow computation, the Levinson-Durbin algorithm uses that special Toeplitz structure to solve the equations step by step. It starts with a really simple first-level predictor and then cleverly builds up the solution from there, one piece at a time. This incredible efficiency was the absolute secret sauce that allowed LPC to run in real time on those little 16-bit chips back in the day.
So we have our predictor coefficients. Problem solved, we can go home, right? Ah, not quite. This is where the clean, abstract math slams right into a very messy real-world hardware problem.
Yeah, you gotta ask,
If we have these awesome coefficients, why not just plug them straight into our synthesizer filter and call it a day? Well, the problem is something called quantization error. See, on a 16-bit chip, you can't store numbers with perfect precision. You always have to round them off a little bit.
And as you can see here, these direct form coefficients are incredibly sensitive. A tiny little rounding error can make the whole synthesis filter go haywire and become unstable, which means you get this awful loud screeching sound. It's a disaster. So to fix this, engineers turn to something called reflection coefficients. These guys are way more robust, and they have this fantastic property. As long as their value is less than 1, the filter is guaranteed to be stable. Problem solved.
And that leads us to the super elegant engineering solution, the lattice filter. Now, what's so brilliant about this is that those stable reflection coefficients, they're a natural byproduct that just pops out of the Levinson-Durbin algorithm we just talked about. It's like they come for free. This allowed engineers to design a filter that uses these robust coefficients directly, creating this perfect marriage of math and hardware that guaranteed you'd always get stable, clear speech.
Okay, we've gone through the model, the math, the engineering headaches. Now let's get to the good part. Let's see the payoff and actually watch this filter do its job.
So let's break down what we're seeing here. On the left, that's the spectrum of our source signal, our buzzer. Notice how it's basically flat. It's got energy at all the frequencies like a boring, monotone hum. In the middle, that's the frequency response of our LPC filter, which is shaped by those coefficients we worked so hard to calculate. And when you pass the buzz through the filter, you get the final result over there on the right.
The main takeaway here is that the filter acts like a sculptor. It takes that flat, boring buzz, and it carves away some frequencies while amplifying others. It imposes its own resonant shape onto the source. Those peaks that it creates, those are the formants, and it's the specific placement of those first few formants that shapes a generic buzz into a clear ah or an e or an oo sound, the very building blocks of speech.
So think about it. From a simple buzz in a tube, we get speech. This powerful idea, using a predictive model to capture the essential shape of a sound, it goes way beyond just talking toys. It's at the heart of how our cell phones compress audio, it's in music synthesizers, and it's even used to analyze musical instruments. It really makes you wonder, right? What other complex, amazing sounds could we build from this simple mathematical model?